There are two methods of resolving celestial observations to determine a line of position. The first should be used if the altitude of the observed celestial body is 85 degrees or more. Let's say it is 87 degrees. In other words, it is almost directly overhead or near your zenith. The angular distance of the body to your zenith is called zenith distance. In this case, it equals 90 degrees minus 87, or 3 degrees. This can be translated into linear distance on Earth, the distance in nautical miles from the body's geographic position to your position. 1 degree equals 60 nautical miles, so 3 degrees equals 180 nautical miles. To locate your line of position, you must first determine the coordinates of the GP. The GHA and declination of the celestial body can be found in the Air Almanac. They can be translated into latitude and longitude of the GP on Earth. You then locate this point on your chart. With your dividers, you can measure off 180 nautical miles. Then, you can scribe a circle or segment known as a circle of equal altitude. This becomes a celestial line of position. You are somewhere on its circumference. To get a fix, you must take at least one more observation of a celestial body, preferably 2. This is a very simple method to locate or plot a line of position. Usually, however, you will be observing celestial bodies with altitudes less than 85 degrees. Bodies whose geographic positions will be hundreds or even thousands of miles away from your own position. Theoretically, you could use the first method to plot your line of position if you had a large enough chart. But obviously, you need an alternate. There is one, and it is called the intercept method. As with the first method, it may begin with an observation with the sextant to determine the sighted altitude, or HS, of a celestial body above the horizon, and a notation of the date and Greenwich Mean Time of the observation. This observation enables you to determine corrected observed altitude, or HO, an important factor you will use in a few moments. Now you begin computations by finding the geographic position of the observed celestial body. This means determining its GHA and declination on the celestial sphere. Then, translating those coordinates to latitude and longitude on Earth. Then you assume a position for yourself on Earth, somewhere near your DR position. In the intercept method of celestial solution, you determine and locate your actual line of position relative to your assumed position, instead of the GP of the celestial body. This involves the solution of a celestial triangle brought down to Earth. The points of the celestial triangle are the celestial body, the celestial pole of the hemisphere you are operating in, and the zenith of your AP. On Earth, the points become your AP, the GP of the celestial body, and the appropriate pole. As you remember from your geometry, if you know the length of 2 sides and the included angle of any triangle, you can quickly determine the other side and angles. If you know the declination, you know this side, co-declination, or polar distance of the observed celestial body, 90 degrees minus the declination. If you know the latitude of your assumed position, you know this side, co-latitude, 90 degrees minus the latitude. This angle is the LHA, local hour angle, of the celestial body. It is measured from the celestial meridian of your AP westerly to the hour circle of the celestial body. In this situation, LHA of the celestial body equals its GHA minus the longitude of your AP. If your AP were here, east of the prime celestial meridian, you would add the longitude of your assumed position to the GHA of the celestial body to get the LHA. So if your AP is east longitude, you add the longitude to GHA to get LHA. If it is west longitude, you subtract longitude from GHA to get the LHA of the body. However, in this west longitude situation, where the AP is west of the observed celestial body, LHA is this angle. Remember, LHA is always measured westerly 360 degrees. In this case, you can compute LHA by taking the GHA of the body, adding 360 degrees, then subtracting the longitude west of the AP. The remainder is LHA of the celestial body. But back to the first AP we considered and the solution of its celestial triangle. Most of the computations have been done by mathematicians who have created tables designed for three inputs: LHA of the celestial body, whole degree of latitude of your assumed position, and declination of the celestial body. With these three factors, you can turn to your HO 249 site reduction tables to find two important factors. First, the computed altitude, called HC, from your assumed position to the celestial body. HC is the altitude you would observe with your sextant if you were actually at your assumed position. When you have HC, you can compute the co-altitude, or zenith distance, the third side of your celestial triangle. This gives you the linear distance from the GP of the celestial body to your AP. Or, in other words, the radius of the circle of equal altitude from the GP to your AP. The HO 249 tables also give azimuth, the interior angle of the triangle of your assumed position. This angle is referred to as Z. You must then convert Z to true azimuth, or ZN, an angle measured clockwise from true north. A reminder for converting Z to ZN is found in the upper and lower left-hand corners of each page in the HO 249 tables. If true azimuth were plotted on a chart, you would have a line running from your AP toward the GP of the celestial body with a segment of the circle of equal altitude perpendicular to it through the AP. This segment is represented by a straight line because the radius of the circle is so great. With ZN, or true azimuth, you can now begin to locate your actual line of position. You know HC, the computed altitude of your assumed position. You also know HO, the corrected HS, or sighted altitude of your actual position. Suppose these are the actual figures. HO is 45 minutes of angle greater than HC, or, in other words, there are 45 nautical miles difference in radius between the circles of equal altitude, measured along the true azimuth line. But in what direction? Remember the basic principle of altitude measurement. The larger the angle, the closer you are to the GP. The lesser the angle, the farther you are away. In practical terms, if your HO is less than the HC of your assumed position, you are farther away from the GP of the celestial body. If HO is more, you are toward or closer to it. Just remember ho, mo, to. Ho, more, toward. Ho, mo, to. Think of the happy Japanese navigator, Lieutenant Homo-to, smiling over your shoulder. In this case, HO is 45 minutes of angle more than HC. Remembering homo toe, you know you are 45 nautical miles toward the GP of the celestial body. This is called intercept. The line of position is plotted as a straight line representing a segment of your circle of equal altitude with a barb at either end of the LOP, the name of the source on top, and the time of observation beneath. Two other LOPs derived from observations of two other celestial bodies will give you a positive fix. This is how the intercept method works in theory. We will see how it works in practice in part 4 of this series.